Hi, good morning everyone. I'm audible.
Yes, you are audible.
So, on the behalf of Integrated Microsystem, I thank you all for joining us today. I sincerely appreciate your participation in the fifth session of our faculty interaction webinar series on the topic Computational Insights into the Magnetic Behavior of 2D MX with Synopsys QuantumATK software. It is my pleasure to introduce today's esteemed speaker, Dr. Suranjan Shil. Dr. Shil is currently an assistant professor in the Department of Chemistry at Manipal Academy of Higher Education. He has made significant contributions to various fields, including magnetic molecules, molecular electronic transport, thermochemistry, reaction mechanism, organic solar cells, and machine learning. His expertise lies in advancing magnetic material and device applications through cutting edge computational research. With a strong foundation in the theoretical and computational physics, Dr. Schill has extensively worked on the electronic, magnetic, and transport properties of 2D materials, particularly MXenes, along with modeling and simulation of magnetic devices. In today's session, Dr. Schill will share his research insights on utilizing Synopsys QuantumATK software for exploring the magnetic behavior of 2D MXenes. His talk will highlight how atomic scale modeling and simulation technique can drive innovation in this field. Following the presentation, we will also have a live demonstration on the same topic by Mr. Deepak Upadhyay, Application Engineer at Integrated Microsystem. He will provide a hands-on walkthrough of Synopsys QuantumATK software, showcasing its practical applications for studying magnetic behavior in 2D MXC. With this brief introduction, I am delighted to hand over the session to our esteemed speaker, Dr. Suranjan. Over to you, sir. You can share your screen.
Thank you for your kind introduction. So first, let me share the slides. My slides are visible?
Yes, sir, it is visible.
Okay. So, good morning, all of you.
Kindly share the full screen, sir.
Sorry?
Kindly share in the full screen mode.
Okay. It's not getting full screen now.
You can move to the right side bottom.
Right side bottom.
Bottom right side. You can available option there. Next one, right side. Next one. Just beside the side sound or visualization.
This one.
This. Right.
Where else?
No.
Good morning, sir. Just go to slideshow view. That is enough.
Slideshow view, but I'm not getting.
Right side bottom you have na scroll bar. Left side that one.
Okay.
Next back.
First icon. Next to
back.
first icon from left.
Okay. Yeah.
Apart from this, right? Left side.
No.
Left side first.
Adjacent to minus sign.
Yeah. Adjacent to minus sign on left side.
Just a second.
Bottom right.
Bottom.
Sir, at the top
right.
you can see there is one option at the slideshow. At the top. At the top toolbar.
Top. Just a second.
Sir, in the menu, top menu slideshow is there na?
Sir, let me show you how you can share. Let me show.
Slideshow.
Now you can present your screen, and here you need to click on this here. Either this one you can click, and here you can see this is the slideshow option. So once you click on this arrow, then you will get the full screen.
Yeah.
Right. Now I,
This screen. Can you
now I got
Sir,
now?
here there is one option that is the slideshow. This one.
It's not working here. Entire screen. But not coming. Entire
Sir, also one more option at the top. You can see there is a one option slideshow at the top toolbar.
Can you see now?
Yes, yes,
yes.
Okay, thank you. Sorry for the. Actually, I was not used to the Google Meet. Okay. So, good morning. So, today I'm going to talk about the computational insights into the magnetic behavior of 2D MXenes with Synopsys QuantumATK. So, I designed my talk in such a way that initially I will show some slides of QuantumATK as Deepak gave me, and then I will go some of introductory slides about MXenes and magnetic properties of MXene. Then some slides I'll show about our work, what we do actually. So first, the Synopsys QuantumATK simulation software. What we can do lots of things. Actually, we are using also from bulk to circuit. So we can do the bulk materials for any kind of materials, transistors, and nanoelectronic devices like spintronics and electronic transports. And we can design the transistors, magnetic RAM, many kind of things, and all those things we can do with different levels of theory based on the size of the systems, like density functional theory. You can use semi-empirical, we can use the force field methods. And then the good thing actually about QuantumATK is that it has a very nice interactive graphical interface. So for a beginner like us, when we started 2 years back, then if you don't know anything, still you can work with the graphical interfaces. So you can build your input files, and you can analyze the results in the same screen actually. So like other free softwares where the graphical interface is the difficulty, here is not. Here the graphical interface gives you a very nice view, and you can do anything what you want with the material and also analyze the results. And then the most important part, what I feel actually, the DFT plus NEGF, Green's function method, where we can calculate the lots of things, mostly the device designing or spintronic device design or molecular device designs. And it has many functionalities like band gap analysis, device density of states, projected density of states, and block function. All those things are there, so which you can check. And I think Deepak will give you later more introduction about that. And what we can do the phonon coupling and electron phonon coupling and the phonon scattering, photocurrent, and transmission spectrum, and current versus voltage curve, and also the spin dependent current like spintronics devices. We can do that. So now we come to introduction to about our work. So what we are doing presently. So we are started with MXenes. So MXenes is a very important material which come in 2011. It's very new field, and many people are working and exploring the applications of MXenes. So MXenes discovered in 2011 by Yuri Gogotsi and Michael Barsum at the Drexel University, and it has a nice properties, and it's a 2D material first of all, and then it has very tunable properties. You can see in this periodic table how we can make this experimentally. People synthesize with this kind of transition metals, and if we mostly the carbides and nitrates are synthesized, the other may be possible, but carbides and nitrates are the most available MXenes, and they have the general formula like n+1 xn and tn. T is the termination, meaning that when you are making a 2D materials of MXene, let's say metal carbide, and you need to terminate the surface with some other material, other atoms. It's mostly the non-metals. If you can see here in this right side of the periodic table, phosphorus, sulfur, fluorine, this kind of atoms, you can terminate that and you can make a nice 2D MXenes. But here they have lots of properties like they use for solar cells and battery, many things. But we are especially interested about the magnetic properties, which is not so common in MXenes. But there is a report in 2013 by Kazai, that group, and they investigated the MXenes with metal carbide, with scandium, titanium, vanadium, chromium, zirconium, niobium, and tantalum, and M2N with titanium, chromium, and zirconium, with fluorine, hydroxyl, and oxygen surface termination. So what they found actually, if you can see these tables, and chromium carbide, and they found that magnetic moment when they terminate this termination of the surface, they got 2.71 Bohr magneton, and with hydroxyl termination they got 2.24, but with oxygen termination they got a non-magnetic behavior. So there is no magnetic moment. There is energy difference between the ferromagnetic and antiferromagnetic state is 0. And for nitride, they got magnetic behavior for all three terminations, the fluorine, hydroxyl, and oxygen. And that means it says that this termination, surface termination, is a very important parameter here. And as you can see, this chromium carbide, we see 0 magnetic moment when we terminate with oxygen. But when in chromium nitride, we got some magnetic 2.50 magnetic moment. So which means that we have a tunability based on the surface termination, by which atom we are terminating the surface. That plays a very important role in the magnetic properties. And there is another report in 2020 by a group of Tan, and what they see that this chromium carbide, when they terminate with oxygen, they got ferromagnetic semiconductor. If you see here in the left side, the band structure of spin up and spin down electrons. In spin up, they got 0.55 electron volt band gap, but for spin down, they got 2.19 electron volt. But when it's a chromium nitride and terminated with oxygen, they got a half metallic behavior. If you can see in this spin up electron, they crosses the Fermi level, but in oxygen termination with chromium nitride, they have a band gap here. So in the spin down electrons, so which shows that they have a half metallic behavior. Chromium carbide is semiconducting and chromium nitride is half metallic when they terminate with oxygen. And again in 2021, this group they summarized the versatile properties of this different MXenes, and they found that this compound like chromium carbide, they show half metallic behavior with band gap 2.85, and they did actually all computationally, and they used the HSE functionals, and they got it ferromagnetic. But when they terminate this with the fluoride, they got semi-conducting behavior with band gap 3.49, and they got it antiferromagnetic. But when they terminate the hydroxyl group, they got antiferromagnetic. But in chromium carbide oxygen termination, they got non-magnetic, but nitride they got antiferromagnetic. Again, for chromium nitride and oxygen termination, they got ferromagnetic. So it implies that this MXenes, that surface termination is a very big factor by which you are terminating the surface. And there is a different properties or different MXenes like carbide and nitride. So, and again in 2021, this one group, they reported intrinsic ferromagnetism in 2-dimensional vanadium carbide, not chromium, vanadium carbide. What they found actually, if you see here in the left graph, so they twisted the monolayer vanadium carbide and non-twisted vanadium monolayer carbide. One shows a hysteresis kind of curve in flux density with magnetization force, and another is straight line curve. So by twisting, you can change the magnetic properties of the 2D materials. So this all the studies gives us telling that how we can change the magnetic properties of 2D MXenes. And in 2022, they recently, what they did actually, they made a double transition metal MXenes. If you can see here, they have a band gap 1.35 here. For down spin, for up spin, there is no band gap. Again, for molybdenum, they don't have, but up spin there is no band gap, but down spin there is a band gap. So these are half metallic. So you can see that this materials has very promising electronic properties like half metallic behavior, conductor, semiconductor. We can twin all these properties based on the surface termination and the metals and the non-metals present on the materials. So now what we do actually, so we have seen that we can twin the magnetic properties. So we are interested that, okay, if we can dope these materials, so what the magnetic property will change. So for that reason, what we choose a chromium carbide with oxygen termination, and we doped with 3 different transition metals, like manganese, iron, and cobalt, and we try to understand the change in their magnetic behavior or magnetic properties. So how we did actually, so what we did, we calculate the energies of the materials in the parallel spins and anti-parallel spin, that means ferromagnetic configuration and anti-ferromagnetic configuration, to see which magnetic structure is stable, that means which magnetic configuration of this material is exist. So what we did actually, we calculated with different DFT methods, density functional method, GGA plus U, when we took the U value equals to 4, HSC 06 and B3. So what we found actually, so in spin magnetic moment, if you GGA, we find very low magnetic moment, and the energy difference between this parallel spin and anti-parallel spin configuration is 0. That means it shows a non-magnetic behavior. But the other method all shows a ferromagnetic behavior, which matches with the literature value. So we go with the HSC06, that functional, hybrid functional, which is reported that it gives a good property or magnetic properties of materials. Then we try to understand the band structure of this material. So if we see here, this chromium carbide when oxygen termination without doping, we see there is no band gap at all. So this is conducting behavior, and we projected density of states. We see both the around Fermi level there is always there is a density. But here also, if we see that in the spin up, there is a continuous band, and here it's very close to Fermi level, the density of states with manganese doped. So now if we see here, and this iron dope, in case of iron dope, we see again this conducting behavior. There is no band gap in the material. But if we do in cobalt dope, so that's important, that in cobalt dope we find a band gap here. So that means we are getting a semi-conducting behavior, as we can see from the projected density of states also. There is no density near to the Fermi energy levels. And now we try to understand the magnetic behaviors with the doping. If you see in chromium carbide, when without doping, we got the energy gap between the ferromagnetic and anti-ferromagnetic configuration minus 0.544, which is ferromagnetic, and spin magnetic moment is 21, around 21 maybe. And if we dope with manganese, we see that the magnetic moment increases. It's 21 to 26, it increases. Again, if we dope with iron, we got increase compared to the undoped. It was 22.1, here it's 24. But if we dope with cobalt, again it increases the magnetic moment. But the problem here is that in cobalt dope, we got an anti-ferromagnetic configuration. That means the anti-parallel spin configuration is the stable one. But fortunately, we got that it is semiconducting but anti-ferromagnetic. So what we can see from here, that if we dope with another metal in this chromium carbide with oxygen termination, we got the change in magnetic moments, and also we see the ferromagnetic to antiferromagnetic changes. That means if chromium carbide with oxygen termination, it's a ferromagnetic, but if we doped with cobalt, we got the antiferromagnetic behavior. We can switch the magnetic properties by doping. But for manganese and iron, we can increase the magnetic moment, but the magnetic behavior remains the same. Those are ferromagnetic. And then magnetic anisotropy energy for chromium carbide and with oxygen termination. If we calculate the magnetic anisotropy behavior, we can see here that in the magnetic anisotropy, all have the in plane anisotropy with this is undoped, this is manganese doped, this is iron doped, and we did not do for the cobalt dope because it's antiferromagnetic. So we only do in case of ferromagnetic materials. We see in all the cases chromium carbide without doping, we got around minus 0.38 or something, but here it goes positive direction. Here also it goes positive direction. That means when you dope this chromium carbide with another metal, the electronic structure changes, and we can see that magnetic anisotropy value increases in the positive directions. So that means we can change the magnetic anisotropy value little bit with the doping with manganese and iron. Now we come to the analysis of orbital contribution for the magnetic behavior. What we see here, without doping, we can see this dxy and dx square minus y square, they have the mostly negative contribution in the energies. But if we dope with manganese, what happens? This value here you can see 0.04 minus 0.04. Here is around minus 0.03. That is, it increases in the positive direction. That means it goes less stabilized. And also you can see here in that structure without doping, we have very negligible contribution from the oxygen. But here we can see significant contribution from the oxygen, which signifies that after doping with manganese, the hybridization of the system or the atoms changes and different orbital contribution mix up compared to the non-undoped material. Here in case of iron doped materials, we can see here this energy also increases, and also we can see here the significant contribution comes from the oxygen compared to the undoped materials, but it reduces compared to the reduces for carbon. You can see here it's undoped, there is a significant contribution for carbon, but here is very less contribution compared to this undoped one. That means in oxygen increases, but this is carbon is decreases, and here is also this oxygen, this positive direction. That means it's a vacant orbital, it gets stabilized, it gets filled. And now the Gilbert damping calculations, what we can do actually. So Gilbert damping tells us about the stability of the magnetic states. So that using QuantumATK, we can calculate this important parameter, which tells us about the stability of the magnetic states. So if we see here in this plot that we have the chromium carbide structure, and with this orange curve is related to the manganese dope and green curve related to the iron dope. And what you see when we have undoped materials, you see this curve is not completely stable, but compared to this there is less fluctuation. So it has, but when we dope with this iron and manganese, we can see that magnetic Gilbert damping tensor increases, and if we go to the higher broadening zone, there is no such changes. So at the lower broadening zones, we can see the changes, which signifies that if we dope with this some other materials, other atoms in the chromium carbide MXenes, we can change this magnetic state, the stability of the magnetic state. So here we are not getting that much stable configuration, but we can do in future that, and we can dope in such a atom that it can get more stabilized and the curve got linear. So we need actually a linear curve for this stability of the magnetic property. But here no one is that much stable. But without doping, it is quite little stable compared to the doped one. So that means the doping destabilizes the magnetic state compared to the undoped one. And this in QuantumATK addresses key materials, and which you can see the semiconductor, batteries, solars, and fuel cells, polymers, catalysts, metals, and ceramics, and glasses. So this material, this can be, Deepak can introduce you more about that. And so I should acknowledge ACRB, who gave money to purchase the QuantumATK, and Manipal Academy of Higher Education, who give money to purchase the computers, and also the people who is doing the work. This person Abhinav did all this calculation what I showed here. And thank you for listening. And it's open for question. You can ask questions.
Hello.
Yeah.
So you said doping stabilizes the magnetic state. Is it because of like the Gilbert damping, the damping factor that increases? And
I did not say stabilizes. I said destabilizes actually, because undoped one, if you see in this chart, compared to that, it's more fluctuating compared to this one.
okay,
This
okay,
is the opposite one actually. But
okay, sorry.
It may be some atoms we can find that which can stabilizes also. We can
Okay,
find it here, but we can find it.
thank you, sir.
Hello.
Yes.
Am I audible?
Yes. Yes. Audible. Please.
Actually, my question is like in terms of doping perspective.
Yes.
For example, we will dope electro in QuantumATK. There is an option called spatial region and upper spatial region, that is doping, where we can directly dope N type or P type, and we
Yes.
can give some value in
Yes.
1 to the
That I
power
know.
19.
Yes.
So my question is that, for example, we are dealing with cylindrical gate all around FET kind of technology. So whether it is NIN or means intrinsic channel or somewhat dope with less amount of doping concentration, it will change the it will change the characteristics of IV of any kind of FET or kind of things.
Yes, I think so. I did not show it here, the results. We are presently doing this transport calculation of doped materials or this materials. I think it changes. It changes the
And another question is that for example, threshold voltage value of the FET, any kind of technology, it is zero point 0.3 volt. So if we provide VDS, drain to source voltage, 0.05, is it give proper result, or it will show some convergence problem during task execution?
Yeah, actually what happens, so presently we are doing that, so that convergence problem is very prominent in those cases. Actually, for the transport calculation, we are finding difficulties to converge the calculations. That's true, but what you can do actually, what we are trying to do actually, so you can change the voltage, and you can take what is called this, you can change the tolerance values of the convergence. That we can do, what we are doing, but I don't know that much beyond that actually, that point. So sorry, I don't know that much about that. So what I know, I tell you.
Thank you.
Hello.
Yes.
So thank you for such a nice presentation. So about the doping, I have a like we are like on a somewhat early stage of using this platform. So I have a small question. So when we say doping, like so here, let us say you are doping this Cr2 CO2 with iron. So like in a unit cell, like in a bigger super cell, you are replacing like some of the chromium atom with one of the iron atom.
Yes.
but in a semiconducting sense, right? When we have doping, then the doping concentration is usually very small, like 10 raised to the power six
Yes, yes,
times smaller, right?
yes, yes, yes,
So like I'm kind of little bit confused
yeah, that's
how.
true. Yeah, what your question is valid actually here. So in our case, what I showed here, the doping concentration is very high. That's true. What I show here, doping concentration is really very high. But
Okay.
we are also doing some making the supercell bigger size so that doping concentration can go down. So this is a unit cell
Okay.
small size, so the doping concentration is very high. What I showed here.
Okay. And one more thing, like in coming to this quantum ATK, so when we, let's say, when we are like doing some semiconductor and we set some doping, right? So in the semiconductor, let us say if you want to set even a doping of 10 raised to the power 19, and for silicon, like wouldn't it like become the supercell? Like it has to be really super large, because like if you have 10 silicon atomic concentration is 10 raised to power, let's say, approximately 22. So there is a 3 order difference. So how that is being kind of implemented, and like
There
kind
is
of.
actually, I think Deepak can say that better. But what I know, the earlier question someone told no that this in quantum there is an option you can uh, set the doping concentration, doping percentage, without
Yes, sir.
replacing
We will
physically the
demonstrate
atom,
it. Yeah.
without replacing the atom physically. That is there.
Oh,
N-type and P-type
oh,
doping. That option is there
oh,
in
oh,
quantum ATK.
okay. So thank you very much. Thanks for a nice and informative presentation.
Sir, please have a look in the chat box, and there are some queries.
Okay, just a second.
If possible, could you go to the band structure?
Yes. So band structure. No? Band, yes.
Band structure of spin up, spin down.
This one.
Another slide. Not this one, other one.
This
Spin
one.
up, spin down.
This one.
Uh,
This one.
go. Starting slides.
Okay, I understand. This one or no? Another one is
Uh,
there. Here.
uh,
This one.
right. Yeah, right. This is okay.
Uh-huh.
If you can see the figure B.
Figure B. This one. B.
This
This one. Yeah. The spin up.
the
Yeah.
spin up and spin down. There is a huge band gap difference. What is
Yes.
the reason? What is the reason?
Yeah. Actually, this is from this paper. So what they say in that paper. So there is a spin down gap. They say this is half metal because there is a no gap here. The spin down system, but in spin up there is no gap because it crosses the Fermi level, the valence band.
Right, sir.
So,
Right.
yeah. So your question is, so why this is the difference?
Why it is a significant difference?
And
What
it's
is
a
it?
significant difference compared to this is semiconductor. This is half metal. Because if you see this two structure, this is for only chromium carbide oxygen termination. This is chromium nitride.
Right,
And
sir.
so it's my belief that this is here chromium nitride, the hybridization is coming from the electronic structure. So hybridization with chromium and nitrogen, and when we terminate with oxygen, that makes a huge difference, because this hybridization with chromium and nitrogen, that's the main difference which can give you these results. That's what as I know. But I think you can go to this paper and then see that. This is not our paper, first of all. This is
Okay, sure. Thank you. Thank you for your answer.
Hello, sir. Am I audible?
yes, audible, please.
Sir, so my question is that for the multi-layer simulation, like up to what layer is it valid?
Meaning multi-layer meaning you are saying that you are keeping this material one after another.
Yes, sir.
Okay, so valid means valid in that sense. Valid what? Valid
Means
meaning what?
up to what layer we can simulate here? That is I'm asking.
We can say that depends on your computers. So your computing power. That's the point. So if you have a very big supercomputer, then you can take a very big structure. And if you have a very small workstation, then you can't do. That's what we are facing now, actually. So if we take a very big supercell, then you can't take that, calculate actually.
Oh, okay.
There is some relations actually. You can see in QuantumATK how much atoms you can calculate and how much memories you need. So presently we are doing in CDAC Bangalore computer, in their computer. So it has a huge structure and a huge memory. So we are not facing that much problem.
Okay, sir. Got it, sir. Thank you, sir.
Sir, could you go to the magnetic anisotropic energy?
Yes. Yeah.
Sir, here the negative energy, what it is indicates?
A negative in anisotropy meaning what? Anisotropy meaning that when you can this change the magnetic it's a direction of the magnetization. So that means more negative means you need less energy to magnetize the system.
Okay, sir. This calculation purpose, which pseudo potential is more suitable?
No, we did it in LCAO. We did not use zero potentials here.
No, I'm talking about that what we call pseudo potentials, that GGA, LDA,
No, okay, no,
that
that's
kind
it.
of
But
pseudo potential.
with
Which suitable?
functional, you can say with functional. Okay.
Yeah, functional.
So normally hybrid, people say hybrid is the best one, but it depends on the structure. If you have a very big magnetic structure, then hybrid may not be that useful because in computing power point of view. So then GGA plus U, it gives quite a reasonable result, but not pure GGA. GGA plus U, you need however you require to get the correct structure.
But for spin orbital coupling, it will take a long time. It is a major
yeah, of
problem.
course, definitely it takes long time. Again, it depends on your computing power.
Right. So mainly the accuracy is depending on what are the parameters, sir?
Accuracy depends on, first of all, functional and basis function, and DFT basis function don't depend that much on the basis function, but functional is the one thing which depends. So hybrid, it gives quite reasonable results. In DFT calculation, this functional is the main responsible here.
Is it better option if I use GGA minus of or meta GGA? That is
No, then
it?
GGA plus U is fine. If your computing power is very not that great, then GGA plus U, if I show you, let's say here, you can see here, the GGA plus U gives us this ferromagnetic behavior, and SSC, B3 leaf, all this hybrid functional gives a ferromagnetic behavior, but only GGA, it don't give you. So I think meta GGA also, I don't know meta GGA how much it will give, but again, I think I can say that GGA plus U is good for the solid state and periodic calculation. GGA plus U give a good reasonable results. If you see the literature also, you will find that GGA plus U gives a reasonable results. But it's better if you can go HSC or bit relief also. Yeah, please.
Which will take the less computational cost out of these all methods?
GGA takes the less time, but GGA is not that correct. So you can go to GGA plus U, which is take the less time compared to HSC and bit relief. This is takes the less time, GGA plus U, compared to HSC and bit relief.
Thank you, sir.
Hello, sir.
Yeah.
Sir, what is the difference between density functional theory, semi-empirical calculation, and force field calculations?
Okay. So DFT, what does it mean? DFT uses the density functional theory. Do you know Hartree-Fock and all those things?
Yes, sir. Yes, sir. I have. Yes, sir.
You know that in Hartree-Fock is not correct because correlation is not there, and so then we can go to the ab initio, this post Hartree-Fock, cache CF, cache PT2 for molecular calculation, but those are very expensive. So you can't. It's really expensive. Normally, people for molecules also we don't use, but for solid state, if you go for DFT uses the concept of density of electrons.
Yes, sir.
So in normally in Hartree-Fock and other post Hartree-Fock methods, what we use, you use, if I say in a simple language, in each electrons you have 3 coordinates. So if you construct the Hamiltonian, it's a very huge structure of Hamiltonian. But if you can't solve it actually. You can solve it, but it's a very expensive thing. But if you go to DFT, it's a single particle theory. So all the electrons become one density. So this your equation becomes much simpler compared to sorry. So it becomes much simpler. So you can use the DFT. And semi-empirical means what? Semi-empirical means you are taking some properties of experimental data from the experimental data. Some data is taking from experiment. Let's say, for example, bond length, carbon-carbon bond length. So we are considering, okay, carbon-carbon single bond length 1.54, whatever. So this is already taken. It will not calculate it. So it will already inbuilt in that, so your program or in your method. So that's the semi-empirical method.
Okay, sir. Thank you, sir. And force field?
Sir, please have a look in the chat box.
Okay, okay. A force field is very simple method actually. You can do a force field is very simpler method. Now, mostly we don't use that actually nowadays.
Okay, sir.
Sir, good morning.
Thank you, sir.
Good morning.
Sir, I have a question. Actually, how can you differentiate the magnetism, like ferromagnetic and antiferromagnetic, with the spin moment values? Is there any other category?
No, what we calculate it that we calculate the energy of two configurations: parallel spin configuration and anti-parallel. That means we are forcing the system that okay, you all the electrons spins will be parallel, and another way we make it anti-parallel, and then we calculate the energy. We optimize it in the two configurations, and we find the which is the less stable configuration. Then we say okay, this is the stable configuration. If it's ferromagnetic, we say it's ferromagnetic. If it's antiferro, it's antiferro. Yeah.
So, like in the collinear calculation, right?
Yeah. Yes. Non-collinear also you can do. Normally we did collinear here.
Okay. Then when we start the collinear calculation, that means we are assigning spin value alternatively to each atom for identifying where for fixing it as a antiferromagnet, right?
Yes. We are alternatively antiferro means we are keeping the one is spin plus one and one minus one. That way we are defining.
That we need to define in the QuantumATK, right?
Yes, yes, yes. Initial spin we have to give.
Yeah, initial state we have to give, right?
Yes, yes.
Okay.
We need to define the initial.
So then we need to compare. Then we need to compare those two. Then which one is minimum? Then we can identify the magnetic behavior of the material, right?
Yes, yes, yes. That's it.
Okay.
Hello, sir. Yes, yes. I'm checking the chat box. The magnetic moment for that is pretty Meher. The magnetic moment of the compositions are pretty higher. Is it per unit cell or formula unit? It's per unit cell. It's per unit cell. Pretty Meher. Another question: doping in what amount and what is target structural site for the dopant? Was there any pattern of investigation adapted for amount of doping and target sites? Yeah. So discussion. Another question: doping in what amount and what is the? It's around 6% to 7% we doped actually, and the pattern we use in the corner of the cell, the supercell, what we considered we did actually for this initially, but others we can do in the inside also. That I did not show here.
Excuse me, sir.
Yes.
In GGA plus U method, how to design, how to estimate the U value?
It's user defined, so you can change the U values, and mostly from literature, which is the correct U value for that metal, for example chromium. You can find in literature, and also you can change it yourself and then check which is suited your experimental things better.
Suppose if I am not found experimentally, so
You have
myself,
to depend on the literature. You have to depend on the literature. So let's say for chromium. So
if I want to do myself, how to estimate U value?
Hi, sorry for disturbing you.
Yeah.
Actually, we will demonstrate this application in the demonstration part. How you can define the exchange correlation function, GGA meta, GGA hybrid function, all this.
Okay, then Deepak will answer these questions. I am leaving.
Yes, yes, yes.
So how can the coat or surface modification of graphene CNT be done using PubChem CID-based molecules? You can give just pointer steps. I already know how to extract the molecules from CID. After that, you can guide me this figure.
Sir, we have already addressed this query.
Okay. So how can we get file into QuantumATK? How can we link TCAT file to QuantumATK? That I don't know. If you know, Deepak, then you can answer this.
Sir, actually direct integration is not possible, but we can export the raw data from this QuantumATK software that you can utilize in the TCAD application. Like you can import the material properties like their reflectivity, all these property you can import in the TCAD application.
Okay. How can one calculate the magnetic exchange interaction for magnetic material quantum mechanics? Yeah, you can calculate Heisenberg exchange interactions in quantum mechanics. There is an option called Heisenberg exchange that you can do. Can you please provide the path for CDAC quantum ATK? No, I can't. I can't because quantum ATK is it's my license. I installed in CDAC because CDAC has a agreement with our university. We need to pay CDAC for this their computing time. It's not free for us, but I don't know the other universities. Maybe it's free. But quantum ATK, if you wanted to in CDAC, you have to purchase the quantum ATK.
Yes, sir. This is the commercial software.
This is commercial software. Okay, so see already how to fix easy axis for magnetic anisotropy. How to fix? You don't need to fix the easy axis anisotropy, but your pistol needs to be in this axis. Then you can do that. Is this free software? No, it's not free software. Okay, I think all the questions answered.
Thank you, sir. Thank you for this nice presentation. So let me demonstrate this magnetic property by the quantum
ATK software. Sharing now.
Yes. So this is the graphical user interface of this Synopsys QuantumATK software that is called Virtual Nanolayer. So you can see this is the plugin toolbars where we have the project, we have the data, we have the builder settings, we have the workflow settings, we have the job submission settings, we have the editor, and we have the 3D viewer, and we have the online database. So this is my project that I have created earlier. If you want to work on the new project, you need to select this add option, define the directory, and you can easily create a new project in this QuantumATK. And once you create, you can go to the data section. Here you can see, this is my project that I have simulated earlier. And if you want to filter out, like you can see, this is the filter option. We can filter out everything so that we have created, and also the simulated data. If you want to show only simulated data, you can go with the data option. You can see. You can also add your own filter by selecting this add option. You can define the name. This is the builder section that will basically help you to create any kind of structure, either crystals, molecule, devices. And here you can, this area is called stats. So whatever the structure you will create, that will store in the stats. Sirin, can you mute your mic? Okay. So this area is called stats. So whatever the structure you will create, that will store here. And this is the 3D view. And here you can see we have the advanced panel toolbar. So this advanced panel toolbar basically help you to create or design structure. Here you can see we have the various building tools like the FM cantilever tip structure. You can create the amorphous structure, alloy structure, icosahedron, interface builder, nanoparticle, nanowires, elastic band. And even we have the bulk tool option. So this is the advanced panel toolbar that will basically help you to create or design structure. Here you can see we have the builder tools. We have the bulk tool option as well. Like you can fit the cell, you can merge any two cell, you can repeat your structure. Even you can also stretch your cell, and you can create the supercell structure as well. And here you can see we have the device tool option as well. So you can create your device from the bulk structure. You can also create the device from the surface structure. So today we had the session for this magnetic property of the MXene materials. So For creating the MXene materials, here you can see we have the option. So in QuantumATK, we have the option to import the material from the local database. You can see this is the local database that exists inside the software. We have the list of molecule structure, and we also have the list of crystal structure like the face center cubic structure, body center, simple cubic, hexagonal, orthohedral. So all kind of structure we have in the crystal builder, crystal structure, and you can see these are the fluorines materials, and this is the zeolite materials, and we have the monomers for the polymer simulation, and we also have the ground state element. So first you can try to import your material from the local database. If the material is not available in the local database, then you can go to the online database. So in the online database, you can see we support the crystallography open source database, and we also support the material project. So whatever the material you want to import in your builder section, so first you need to select their element. Suppose I would like to select this chromium and then this carbon. So you can see two element has been selected, and now I would like to click on this search option. Then it will search every possible combination of chromium and the carbon from the material project. Here you can see it has find 9 structures with the different crystal systems like the hexagonal, orthorhombic structure, simple cubic structure, trigonal, and also the hexagonal structure. So whatever the structure you want to import, you can select and go to the arrow and select this builder. You can also download this file, and then here you can see we have the option. We have the from file option, and these are the supported file format that you can easily import in this QuantumATK software, like the Python file, HDF file, .xyz file, CIF file, XSD postbar file, contour file. So this file format you can easily import in QuantumATK software.
Excuse me.
So any kind of, yes sir.
If the what I expected that that the crystal is not available in your list, then how to generate new crystal?
Yes. So if the material that you want to work is not available, neither in the local database nor in the online database, then we have the option plugin toolbars. So in the plugin toolbars, you can see we have the crystal builder, and for creating any kind of crystal structure, you should know the information like the space group, their Bravais lattice, their ABC value, their alpha, beta, gamma value, and also the element and their fractional coordinate point. Then you can easily create any kind of crystal structure. You can see we have the space group, triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, and the cubic structure. So first you can select their space group, like you can see, this is the face center cubic structure. You can define their ABC value. Suppose I would like to go with the 5.41 angstrom. And then you can add the element by selecting this add option, select their fractional coordinate point. So I would like to go with the XYZ. And here you can see this is the default hydrogen element. If you want
Excuse
to
me.
change this hydrogen,
Here,
yes, sir.
how to define this primitive and conventional? You can see the right side of that
So this
small
is the
window.
preview option. So once you define all this information, this is the preview. So like you can see, this is the conventional cell and this is the primitive cell. So this is the option for preview the structure, like the
Okay.
primitive and the conventional.
Thank you.
Now, if you want to replace this hydrogen with any other element, you need to double click, and you can see these are the list of elements. So I would like to go with the gold material. You can see this is the gold, and this is the fractional coordinate point. You can also change the fractional coordinate point as per your need. And here you can add n number of elements. There is no limitation. And once you're done with this crystal builder, you need to click on this build option. So this way we can create any kind of crystal. Now we are going to create a MXene materials. So any kind of MXene materials you can create, like the titanium carbide, vanadium carbide, molybdenum carbide, chromium carbide. So I would like to go with the chromium carbide. So this is the hexagonal structure that I would like to import in the builder. Now you can see this structure has been loaded in the builder, and this is the 3D view. So this is the simple structure. Now, if you want to create a supercell structure out of this CRC, then here you can see this is the advanced panel toolbar, and we have the supercell option in the bulk tool. So this is the supercell, and here you can define the direction. Like I would like to define 2 times in the A direction, 1 time in the 2 time in the B direction as well, and minus 1 time in the B dash, and 1 time in the B direction, and then click on this transform. You can see I have created a supercell structure. And now if you want to repeat your structure in any direction, either direction A, direction B and direction C, so you can see we have the repeat option as well, this one. And here we can define the number of repetition. So I would like to repeat 3 times in the C direction. And then apply. So you can see we have created a supercell structure for this chromium carbide. Now suppose if you want to delete any undesired element from this structure, so you can select and go to the delete option. So this way we can delete any atoms from the structure. And now if you want to add the functional group element like the oxygen, hydrogen, anything in your structure. So I would like to select this top carbon element and I would like to replace with the oxygen with the functional group. Now you can see the element has been changed. Similarly, I would like to take this element and go with the oxygen. Now you can see I would like to delete this undesired element from this structure. So we have created a chromium carbide with the functional group of oxygens at the top side and the bottom side. Now you can see our structure is ready. And now if you want to simulate this magnetic property of this chromium carbide with the transition of this oxygen, so you can go to the workflow builder. Now you can see this is the created structure that we have done by the builder settings. And here you can see we have the calculator settings. So this is the LCO calculator, we have the device LCO, we have the plane wave calculator, we have the semi-empirical calculator, we also have the device semi-empirical, and this is the classical force field calculator, and this is the ground state calculator that will combine with the many body perturbation theory. So we have created a material structure, so we will go with the LCO calculator. You can also go with the semi-empirical calculator, but if you want to get the higher amount of accuracy, then you can go with the LCO calculator. If you want to optimize compromise with the accuracy, then you can go with the semi-empirical calculator. So this semi-empirical calculator is faster than the LCO calculator. Now if you want to change any parameter setting in this DFT LCO, so you can see these are the basic parameters that we need to define before the simulation. If you want to define any kind of a spintronics application in your structure, you can see this is the spin, like the unpolarized, polarized, non-collinear, and non-collinear with the spin orbit coupling. So I would like to go with the non-collinear with the spin orbit coupling, and here you can see this is the exchange correlation function that we have in this QuantumATK, like the LDA, ZGA, meta ZGA, hybrid function, and this is the custom option. So once you select the exchange correlation function, then you can select their predefined functional set, like you can see this is for ZGA, and if you select the meta ZGA, you can see this is the predefined functional set for the meta ZGA, and this is for the hybrid function as well. So I would like to go with the ZGA, and here you can see this is the pseudo potential method that we have non-conserving and the power potential. You can also define the numerical accuracy like the occupation method. You can also define the temperature. You can also define the density cutoff energy, and then go with the K-point sampling method. Here you can see this is the iteration control where we can define the tolerance, maximum iteration steps, their damping factor, and also the number of history per steps. And you can see this is the Poisson solver, so that you can define the boundary condition for any structure like the direct conjugate gradient, non-uniform with the conjugate gradient, multigrid, fast Fourier transform, and fast Fourier transform for the 2-dimensional. If you select the multigrid here you can see we have the periodic option like the periodic and also the Dirichlet boundary condition. You can also define the non-von Neumann boundary condition as well, this one. So we have done the LCO calculator settings, and now for the magnetic property and the electronics property. So before the property simulation, we want to optimize your structure. So we also support the optimization of the material and the optimization of the devices, that is also possible. You can search the optimization. You can see this is for the material and this is for the device. So we will add this optimized geometry for the material. And here you can see these are the parameters that we need to define, like the force tolerance. You can enable the optimized cell, steps error tolerance, maximum number of iteration steps, maximum step size, and also the optimization method. So once you define all these settings, you can go to the analysis part. So I would like to add the electronics property like the band structure, density of state, and also the projected density of state. And we will also move to the magnetic properties. So let me search the band structure. Now you can see band related like band structure, complex band structure, effective band structure, fat band structure. So I would like to add this band structure, and here you can see these are the settings. Like you can define the point per segment, and also you can define the line zone route, interpolation method, and also you can define the band above the Fermi levels and also band above the absolute energy. So this is the band structure, and also I would like to add the density of the state. So this is the density of the state, and here you can see this is the projected density of the state. So in the projected density of the state, you can see this is the projection. Here we have the spin up and spin down. We have the spin in the XYZ coordinate. We have the site and cell. We have the site and orbitals, and we have the tag option. We have the element and the element and cell, and the element and orbital as well. So based on your need, you can select and then go to the magnetic properties. So here you can see we have the magnetic anisotropic energy, and here you can define the theta angle, phi angle, and also the projection. Here you can define the energy range and the band per electrons, and then K-point sampling method. So once you define all the setting, you can move to the Gilbert damping. So this is the Gilbert damping that we have added. So our workflow is ready. Now we can define the file name and then go to the editor. So here we need to define the file name, and here you can see this is the script that we have generated by defining the workflow settings. So this Python file is editable. So before simulation, if you want to change any parameter in this Python file, then you can change, and then you can move to the job submission settings. So this is the job submission settings. We need to save this Python file, and here you can see this is my local machine. So in the local submission mode, we have the serial. It will run on a single core. You can also define the number of thread by selecting the threaded parallel. And if you want to define the number of thread and number of processor for the faster simulation, then you can go with the multi-process parallel. You can go with the machine settings. You can also manually define. So this is for firing the job from this GUI to the local machine. And if you want to fire the job from GUI to the remote machine, you can see this is the machine setting option. We support the new direct remote machine, local machine. This is the LSF, and this is the previous machine, and this is the PVS Pro, this is the SG, and this is the Suranjan machine. Like you can see, this is the previous machine. Here you can define the host name, the port, the username. So once you define in all the machine setting, then you can add a new machine here, and then you can easily fire the job. So this is our job that we have added, and now you can see the state is pending. If you want to simulate this job, you need to click on this run button. Now you can see this state has been changed, and it is under running condition. And once here, it will generate the log file. So in the log file, you will get all the information, background information, whatever the simulation is ongoing for this structure. So I would like to stop this structure because I have already simulated. So this is the procedure for simulating the magnetic and also the electronics property of the MXene materials in this QuantumATK software. Even you can also calculate the transport property of the magnetic devices. So let me cover the device application as well. Suppose you have created this structure, this MXene materials, and you want to convert this structure into a device. So before going to the device part, we need to repeat our structure so that we can define the electrode and also the center region. So here you can see this is the repeat option. So I would like to repeat 5 times in the C direction and then apply. Now you can see our structure has been repeated 5 times in the C direction. And here you can see we have the device builder. So this is the device from the bulk structure, and you can see it has automatically selected the minimum electrode length for the left side and also the right side. And this is the electrode extension length. So this electrode extension length basically will help you to reduce the scattering between the electrode and the center region. So this way we can reduce the scattering. And if you want to define the buffer region in your device structure, so you can see this is the buffer for the left side and the right side. So once you're done with this device builder, you select this OK. And suppose you want to define any kind of doping, like the N-type doping, P-type doping, and also the elemental doping. So here you can see this is the doping for the N-type and P-type. So we need to select our region where we would like to add the doping. So I would like to add this left side as a n-type doping. Here you can see this is the n-type doping. Here you can also change the concentration value, concentration. So this is the left side that we have added, and this is for the center region. Here I would like to add the p-type doping, and I would like to select this right side as a n-type doping. You can see we have created a NPN transistor. You can also change the value as well, and the unit as well you can change. So this way we can add the n-type doping and p-type doping. And if you want to add any kind of doping effect in your MXene materials, so this is the device that we have created, and this is the material. So if you want to include the iron, cobalt, some things in your structure so that you can define the doping of that particular element. So I would like to select this element and go to the periodic table. So from this periodic table, we would like to go with the iron first. You can see we have replaced this chromium with the irons, and then you can study their properties. Same property you can study like their band structure, projected density of state, and also the magnetic properties, so that you can find the difference between the by adding the doping and without the doping in your structure. And we have one more option in the workflow settings. You can see if you want to define the collinear spin some things, so you can also go with the calculator settings. Like here you can see non-collinear, and if you want to define the magnetic moment for any particular element, so you can go to the initial spin. So you can see this is the initial spin that we will add after the calculator. And in the initial spin, you can see we have the spin type like the collinear and also the non-collinear spin. This is the method by value, and this is the change spin for the atoms. Like you can see, these are the element and their scaled spin value. So if you want to treat your material as a ferromagnetic, then you can define the scaled spin as a 1. And if you want to treat your material as a antiferromagnetic, then you can define -1 and then apply. Now you can see. So this way we can also set the spin application in your material and also the devices. Now if I show you the result that we have done for the chromium carbide with the functional group oxygens. So let me go to the data, and here you can see these are the simulated data. Now you can see with the doping of iron, this is the optimization that we have done. Sorry, I think the structure is not simulated fully. So let me open one more project. Yeah, this one. Yeah, here you can see this is the by doping the iron. This is the optimization that we have done. Here you can see this is the iron materials. So we have the graph over the energy, force, and the stress with respect to iteration step. Here you can see we can also play and see the changes in the structure. So this is for the doping by adding the iron, and here you can see we have simulated without doping, and here you can see this is the band structure that we have. Now if you want to show the plot, you need to double click. Now you can see this is the band structure for this chromium carbide with the functional group oxygen, and here you can see the direct band gap value is 0. So let me go to the advanced analysis. This is the y-axis, and I would like to change the upper limit and the lower limit as well. So I would like to go with the from -1 to 1. So you can see this is the band structure without any doping. Here you can see we have the Fermi energy, and this area is conduction band, and this is the valence band. So we have simulated this material with the default parameter. Once you define all the accurate parameter, then you will get the exact result. So this is the density of state that we have done for the same materials. Here you can see this is the density of state with respect to energy from minus 60 electron volt to 60 electron volt. So this is the projected, density of state. We have also done the projected density of state. And here you can see this is the Gilbert damping. Here you can see this is the this is the temperature, and this is the damping constant, and this is the damping rate. This is for the 0.01 electron volt, and this is for 0.019 electron volt. So this is the report for this Gilbert damping, and let me show this magnetic anisotropic energy as well. So you can see this is the magnetic anisotropic energy. Here you can see we have the total magnetic anisotropic energy, and we have also for the carbon, we have for the oxygen, and we have for the chromium as well, and this is the 0. You can also go with the projection. So actually we have done for the site, but we have the option in the workflow. You can see, let me show. Yeah, you can see, you can also change the site and cell, site and orbital, and the no projection as well. So let me show the projected density of state as well. You can see we have done the projected density of state for the same material. And here you can see we have done the spintronics application, like the spin up and the spin down. And this is the total spin. So let me disable this too. So this is the total projected density of state with respect to energy. And if I show you the for the spin up, so this is for the spin up, and this is for the spin down. And also if you want to go for the advanced magnetic properties, so here you can see we have the vampire scripting as well. So for calculating the magnetic property by using this vampire script, you need to import the data like the Heisenberg exchange and also the magnetic anisotropic energy. So once you drop the data, then you can easily calculate the magnetic property, and also you can see this is the simulation type like the Curie temperature, static hysteresis loop, and also the Monte Carlo anisotropic and the field cooling as well. So I have already done this vampire scripting as well. So let me show the data. Yeah, this one. You can see this is the magnetic anisotropic energy, and here we have the graph over the torque with respect to angle. So multiple, you can see temperature we have defined, and this is the free energy versus angle, and we have the magnetic anisotropic energy with respect to temperature, and here you can see this is the magnetization versus temperature, and this is the magnetic anisotropic energy with the magnetization. And if I show you this spin dynamic temperature, so you can see this is the normalized magnetization with respect to temperature, and this is the spin dynamic trajectory. You can see this is the magnetization with respect to time. This is for the temperature with respect to time. This is the magnetic field, and this is the magnetization in the direction of Z. You can also play this. Similarly, we have done for the another structure. This is the temperature magnetization graph. This is temperature graph, and this is the magnetic field, and this is the magnetization, and this is the magnetization in the direction of Z. So I have shown you the maximum features that you can do by using this QuantumATK software for the magnetic and the electronics properties. So if anyone has any specific query, then you can unmute your mic and you can let me know we are here to help you.
Hello.
Hello, Deepak.
Yes, ma'am. Hello, yes,
Yeah.
sir.
So yeah, currently I am working in a multi-component alloy system actually. This high entropy
Okay.
alloy system, and so that I have to generate my SQS structure, special quasi-random structure. So is there any tools in the software from where I can generate my SQS structure?
Yes, ma'am. Here you can see in the advanced panel toolbar, we have the
Okay.
special quasi-random alloy builder. You can click on this create. Here you can define the element and their fractional occupancy and go to the advanced option as well. Here you can define the number of
Okay.
generation, population size, number of the prompt, and also the maximum expansion order. Select this, okay, go
Okay.
to the
Okay.
detail. So we have all types of alloy builder like the SQS alloy builder and also the Hedler alloy builder and also the substitutional alloy builder.
Okay.
This
So
one.
I can generate my structure, no? Yeah.
Yes, ma'am. Yes.
Okay, okay. Or another question is, can we calculate the thermodynamic properties in the software, like the Gibbs free
Yes.
energy and all?
Yes, ma'am. You can easily calculate the Gibbs free energy as well. Here you can see we have the data, and here we have the thermochemistry analyzer.
Okay,
Yeah.
okay, okay. Thank you.
Here you can see once you select all the reaction, reactant, and the product, then you can easily plot the graph for this Gibbs free energy with respect to temperature.
Okay, okay. Thank you.
And also for more thermoelectric properties, you can also go with the transmission spectrum. So let me show the transmission spectrum and the thermoelectric properties. Here you can see. This is the thermal current, thermoelectric coefficient, like the conductance, Peltier coefficient, Seebeck coefficient, thermal conductance, and also the Zt.
Hello, Deepak.
Yes, sir.
Yeah, so you just nice presentation. So first, you in the magnetic simulation, you just mentioned about the Heisenberg interaction. So Heisenberg interaction, I think, can it be calculated directly from the
Yes, sir.
simulation?
Directly you can click. Yes, yes, yes.
Okay.
Here you can see this is the Heisenberg essence. You can add and you can calculate.
So the value will be given for any doping. If you dope it, and the value will be given.
Yes, sir. Here you can see these are the parameters that we need to define for this Heisenberg exchange, like the atomic indices, exchange interaction range, and also the number of contour point, and then K point symbol.
Okay, how this K point sampling is it some user defined things or you are just optimizing
So
this?
this is the user defined. This is the user defined. You can change the value as well. And also you can do the optimization so that you can get the stable configuration. So we have already added the optimized geometry option as well.
And that magnetic simulation, you showed some vampire software, right?
Yes, vampire
Yes.
scripting as well.
So they are doing some Monte Carlo simulation probably. You showed magnetization versus temperature.
Yes, yes, Monte Carlo.
Okay, so that I think you showed in the previous already generated result, right? So it takes some
Yes,
time,
yes,
no? It generates some time.
yes, 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 yes. So first we have to drop the result from the simulated data like the Heisenberg reactions and the magnetic anisotropic energy. So once you've done, like you can see, let me show. This is the I think I have not calculated the Heisenberg. Let me go to the other project as well. So first you have to calculate by Heisenberg actions and also the magnetic anisotropic energy. Then the vampire scripting will be enabled. You can see this is the disable. So once you define the parameter, then it will enable.
And also the magnetic moments also will give, right? The magnetic moments
Yes,
also
yes, magnetic moment you can also define.
directly it will give from the softwares.
Yes. And also, if any like an access part is not available in the workflow settings, then we have the scripting option as well. So here you can also write your own script for any structure, and then you can go with the simulation.
So one more thing. So how do you choosing the supercell? So supercell, is it the band structure or the density of states? Is it dependent on how do you define the supercells? You showed something
Yes,
like
sir. It will also, yes, it also depend
how do
upon
you,
the supercell
so how do you
structure.
choose the supercell which is the right supercell for any particular structure?
Sir, actually, we have done by taking the help of the publication papers. So you can see there are a lot of publication papers that has been published by the QuantumATK. So let me show. This is the QuantumATK documentation paper. Here you can see we have the tutorial, we have the manual, and we have the publication papers. So here you can search the MXene. You can see these are the publication papers related to the MXene materials. So you can go with this UI number. Then it will show you how, like, what kind of supercell structure is required for getting the accurate band gap value.
Okay. So how much time does it require all the simulation that you have done previously
So yeah,
yeah,
let me
getting from
show
the
the
machine also
simulation
I
data.
know roughly how much time it requires to complete?
Sir, actually the time depend upon the number of atoms in your structure and also the system configuration, like for running on the single core multi-core option as well. So let me show the data that we have done. Yeah, you can see we have done the band structure, density of state, Gilbert damping, and also the magnetic and isotopic energy, and also the optimization. So for this structure, you can see it has taken this is the log file, and the log file will get all the information. You can see 2 hours, 30 minutes, and 39 seconds.
Okay. Okay, thank you.
Okay, sir, thank you. Yeah, if there is no query, you can see this is my contact details. So after this session, if anyone has,
Hello.
yes, ma'am.
Hello. Hello, sir. How
Yes,
you
ma'am. Yes, ma'am.
calculated the conductance?
Yeah, conductance part will come in the transmission spectrum. So let me show. So first you have to create a device structure. You can see we have already done a device structure, and then you can go to the workflow builder. And here we need to add the calculator, device calculator, either the device mean calculator, either device also calculator, and then you can go with the transmission spectrum. This one, transmission spectrum. So once the simulation completed, you can go to the data. Here you can search. You can see I have already simulated. This is the transmission spectrum. Yeah. Once the simulation completed, then you will get the conductance value.
Okay, sir. Thank you, sir. One more question. If we want to take gold as an electrode, then how we can generate the device?
Yes, ma'am. Gold-based devices you can also create. So first you need to import the gold material from the database, either the online database. So you can see this is the single unit cell. So you need to make a supercell structure so that you can define the electrode. This is the phase center. Then go to the repeat option. I can see. So this way we can create the gold material, and you can also replace. Suppose you want to replace the gold material in this MXene materials. So you can take the electrode part and go to the periodic table and select this gold material. So let me select the gold. You can see. Now you can see our electrode is gold material.
So,
And then you can optimize your structure, and then you will get the stable configuration for this gold based electrode.
okay, so before the device conversion, we place the gold electrode over the uh, that channel material.
So we have
To
the like different method to add a electrode. Either you can select the material and replace by the gold. So this way you can also create. Either you can take the gold material from the database and then you can design a device as well. So you can let me design the device with the gold based. Sorry, super sim. Then you can repeat. And go to the device builder. So you can see we have created a gold based device. And now you can replace the center region as well as per your need. So whatever the material you want to take, you can replace. And we have one more option. Let me show in the magnetic tunnel junction. So you can see this is the iron. You can easily select the gold material. And here whatever the material you will select, that will come as a oxide material. So suppose I would like to select this zinc material. Now you can see this structure. So we have the different option for creating the structure.
okay, sir, thank you.
Hello, sir.
Sir, I have a question.
Yes, sir. Tell
Hello.
me.
Sir,
Hello.
whether this quantum APK have any student version? Hello, am
Sir,
I audible,
actually
sir?
it comes with the hello. Yes, sir.
Am I audible, sir?
Yes, sir. Yes, sir. You are audible. So, sir, actually it comes with the academic bundle license we have in QuantumATK.
Sir, actually, before purchasing this quantum APK, our students should be familiar with the student version. Then and after then, university sanction that license version of the quantum APK. If it is
Yes, sir.
there
For that we have the evaluation license option as well. A trial license option we
sir,
have.
just let me finish, sir. If it is any student version and it is useful for our students for getting their research and publications, then our university sanction the license version. Sir, is there any student version which is available online, sir?
Okay, sir. No, sir. We will like discuss these things after this session, sir. So this is my contact details. So you can note down, and after this session, we will have a discussion about this.
Okay. So I just note down, sir. Thank you for your wonderful presentation, sir. Sir, I have
Okay,
another
sir. Okay,
question,
thank
sir.
you.
I have another
Yes, sir.
question.
Tell me,
Your
sir.
demonstrated material showed that magnetization actually decreased with temperature. That means this material is not useful for high temperature. So, how can we justify the novelty of your material?
So, sir, let me check the graph as well.
In your demonstration, you showed that.
Okay. So
And my
let me
another
check the graph.
question, what is the change of the corresponding mobility for the change of the magnetization? What is the corresponding change of carrier
Okay.
mobility, sir?
So, sir, actually the magnetic part you need to calculate. So once you calculate the mobility, you can see this is the mobility for the full and for the isotropic as well. So once you done the mobility calculation as well, then you can compare the data for the mobility with respect to magnetization.
Sir, yeah, actually your demonstration showed that the magnetization is actually decreased with temperature. So that is that material is not useful for high temperature. Can you please
So,
show the
sir,
demonstrated graph?
let me check, sir. Let me check. Sir, this one.
No, sir. Not this one, sir. This one, sir. This one. That means after 600 Kelvin, it actually decreased. Okay, so that means that is not useful for the higher temperatures. So what is the corresponding mobility change of the temperature, sir? So this material is not actually useful for the higher temperature. That actually
Yes,
shows
sir.
from
Actually,
the
we have
relative
done.
radiation versus temperature graph.
Yeah, like if you want to stabilize your graph, then you
Hmm.
can include some kind of doping in your structure.
Yes, yes,
So
yes.
this is for without doping. Yeah, you
Without
can say
doping.
this is
That means
without doping.
there is
Yeah,
some
that we have.
change of mobility if we introduce the doping. So what are the changes,
Yes,
sir?
yes, right. So whatever the so actually I have not done any simulation by adding the doping. So once you like done the simulation, then you will show the difference between the without doping and also the by adding the doping in your structure. I think sir already completed this application during the presentation.
Okay, sir, I have another question, sir. Your previous speaker demonstrated that DFT as well as the green function utilization. How can we utilize the DFT and green function by using quantum APK, sir?
Yes, sir. This is the green function method for device application. You can see this is the device LCO calculator, and here you can see we have the device algorithm, and here you can see this is the green function method.
Okay,
So
sir.
for calculating the transport
Yes.
property, we have to include the green function
Hmm.
method.
Okay,
Then
sir.
you can easily calculate the transport properties.
So, sir, that is the utilizations of the green function. How can we use the DFT?
So this is the combination of DFT plus NEGF density function theory
Okay.
with the green non-equilibrium green function method.
Okay, okay. That is a
And here you
included
can see
DFT.
this is the yes, yes. And here you can see this is the only DFT calculator.
Only
So
DFT
this
calculator.
only DFT calculator will not applicable for the device application. So for that device
Okay, sir.
application, we have to include the
That is
DFT
actually
plus
this
NEGF
this
method.
calculation already included in your software.
Yes, yes. We have the option. You can see this is for the material and this is
Okay.
for the device application.
Okay. Sir, another question, sir. In case of optimization, what is the mathematical calculation which is used in backend in quantum MPK?
Yeah, so let me show the manual page as well. You can see this is the manual. And if I show you the, like you can see, this is for the DFT also. So I
DFT.
will share the this manual page as well to you so that you can check whatever the background theory and
Yes.
equations behind this quantum
Okay,
ATK
sir.
software.
Okay, sir. These are the mathematics actually.
Okay, sir. Okay,
Sir,
thank you.
if their user-defined optimization, can we include that mathematical model in your quantum ATK software, sir?
That you can define in the editor part, sir. So you can see this
Editor
is
part. That
the
means
editor.
some
Here you can write your own script.
user-defined optimization model can be also included in your quantum APK.
Yes, sir. Yes, sir. You can also include your optimization method as well.
Okay, sir. Thank you, sir. Thank you. Thank you for your
Okay, sir. Okay, thank you.
answers. Okay, sir. Thank you.
Hello, sir. If we have to calculate the conductance of any sheet like graphene sheet, it's functionalized with oxygen or something, then in that case we can also calculate the conductance using transmission
Ma'am,
spectrum.
yes, ma'am. So first you have to create the device. So once you create any kind of device structure for any element, then you can easily calculate the transmission spectrum.
No. My question is, can we calculate the conductance in a sheet? Only that, not the device. If we have sheet like a structure, in that case we can calculate the conductance.
Like you can see, this is the graphene sheet that we have
Yes,
added.
yes,
And
yes.
if I take to the workflow builder and then go to the transmission, yeah, you can also calculate the conductance for the material as well.
Okay. So have you calculated ever?
I have calculated for the device application, not for the material.
Okay. Okay, fine. Thank you.
Sir, I have another question, sir. Sir, if my
Yes,
collaborator
sir.
having the licensed version of Quantum APK, can I use this Quantum APK remotely?
So regarding, like you can see, we have the remote option as well in this quantum ATK software. This is the
No, no, sir.
local machine and this is the remote machine.
No, no, sir. Sir, is your license having some restriction, local license and remote license?
Sir, it comes with the floating license. If your
Floating
system is
license.
connected by the same local area network, then you can easily use this QuantumATK software at any system.
But is there any chance to, if my collaborator having the QuantumATK license version, then can I remotely access this from my university site?
So regarding the licensing, we will have a discussion after this session.
Okay, sir. Thank you.
Sir, how can we calculate the IV characteristics of the device? Please can you kindly show.
Yes, sir. Tell me.
Sir, how can we calculate the current voltage characteristics of the device?
Okay, so for the IV characteristics, you can take a device structure into the workflow. Yeah, let me show the device. You can see this is the IV characteristics. So first we need to add the calculator. So this is the device calculator. Now you can see. Here you can define the gate to source voltage and their minimum gate to source voltage, maximum gate to source voltage and the point, and also the drain to source voltage as well. Then you can easily calculate the IV characteristics. So I have already done. Let me show the result. Yeah, this one. You can see, and this is the IV characteristics that we have done for the device.
Okay, sir. Thank you, sir. Thank you.
Okay, sir. Thank you. Yeah, so this is my contact details. So after this session, if anyone has any query, they can contact through this number. You can also write the mail. So from my side, thank you so much to all of you.
Yeah, so as we come to the close of today's insightful session, it is my privilege to extend a heartfelt thanks to our esteemed speaker, Dr. Suranjan, for taking his time to share his valuable knowledge and research on computational insights into the magnetic behavior of 2D MXenes using quantum-ATK software. Sir, your presentation was not only enlightening but also thought-provoking, offering us a deeper understanding of how computational tools can be effectively leveraged to explore the magnetic properties of advanced materials like MXenes. We sincerely appreciate the time and effort you dedicated to share your expertise with us. Thank you once again, sir, for making this session a great success. Also, I would like to thank Deepak for showcasing a very live and vivid demonstration of Synopsys QuantumATK software to showcase how we can utilize the software to do various simulation tasks for calculation of various magnetic behavior and magnetic properties. Also, a special thanks to all the faculty members, researchers, and participants who joined us today. Your active engagement and participation are what make this webinar series meaningful and impactful. We look forward to welcoming you all to our next session of the Faculty Interaction webinar series. Till then, thank you once again and have a great day. I think we can end this session. Thank you.
Thank you, Deepak. Thank you.